so I'm going to make a circuit here. And it's going to be an AC wave, AC source with a resistor. And I'm going to say that this resistor is 30 ohms. And I'm going to put an inductor in series with it. And this inductor is going to have 40 ohms of inductive reactance. Okay. We can find out if we want, using the calculator, we can find out the size of the inductor. If we want to know the inductance of this inductor, we can take our 40 ohms of inductive reactance and divide by 60 hertz and divide by 2 and pi 3.1416, and it's 106.1 millihenries, 106.1 millihenries. So that's the size of this inductor. It's 106.1 millihenries, but it's 40 ohms of inductive reactance. And we're going to say we have 100 volts at our source. So here's the thing, when we start plotting this, we're going to see that since it's a series circuit, the current is the same everywhere in the circuit. Just like when we had a series circuit with purely resistive, and we said IT equals I1 equals I2 equals I3 ... Well, this is going to say the total current equals the current through the resistor equals the current through the inductor. IT equals IR equals IL. So the current vector, when we draw it, is going to be on the x-axis. There's my current vector representing the total current. It also represents the current through the resistor and the current through the inductor because it's a series circuit. My voltage drops, however, the voltage drop across the resistor is going to be in phase with the current because resistive loads are always in phase, voltage and the current. So here is the vector that represents the voltage drop across the resistor. And the voltage drop across the inductor, since voltage leads current in an inductive circuit, is going to be up here. There's the voltage drop across the inductor. And there's the voltage drop across the resistor. Well, I'm a little eccentric. I like to leave theta at the origin. I don't like my theta hanging out in space, so I always draw my triangle like that with theta right here at the origin. I just take the vector for the voltage drop across the inductor and I move it out to the end of the resistive voltage drop vector, and I draw my triangle that way. And it's the same with the impedance triangle. We can say that we have 30 ohms of resistance, and again, resistance is always in phase, so it's drawn on the x-axis, and the inductive reactance is drawn on the y-axis. I'm going to start at the end of the resistance vector, and I'm going to draw my 40 ohms of inductive reactance. And now my formula for impedance equals the square root of R squared plus X sub L squared. Because this is a triangle and this is impedance. The hypotenuse is the impedance. It's a Pythagorean's theorem, basically, is what it is. So 30 squared is 900, and 40 squared is 1600, and that's the square root of 2500, and you can check that in your calculator. The square root of 2500 is 50. So it's 50 ohms. That's my impedance. And isn't it nice that resistance is measured in ohms and inductive reactance is measured in ohms, capacitive reactance is measured in ohms, and impedance is measured in ohms. So we have 50 ohms total opposition to current flow. I can write that over here. My impedance equals 50 ohms. Now you might be one step ahead of me. You might be thinking to yourself, well, this guy out of the way. Move this guy out of the way. There we go. Ohm's law says I equals E divided by R, or in this case, E divided by Z. And that's correct. My total current is going to equal 100 volts divided by 50 ohms of impedance. It's going to be a total of 2 amps. That means I have 2 amps flowing through my resistor, and I have 2 amps flowing through my inductor. And if we again use Ohm's law, I can say I have 30 ohms times 2 amps. I have 60 volts dropped across my resistor, and I have 2 times 40. I have 80 volts dropped across my inductor. Well, 80 and 60 is 140. How can that be? I've only got 100 volts. Well, that's because I have to add them vectorially. Vectorially speaking, I have 60 volts dropped across my resistor and 80 volts dropped across my inductor, and my source or total voltage equals the square root of voltage drop across the resistor squared plus the voltage drop across the inductor squared. I know that looks complicated, but take it apart. You'll see it's not that complicated. It's Pythagorean theorem again. We're talking about triangles. So it's the voltage drop across the resistor squared plus the voltage drop across the inductor squared. So 60 squared is 3,600. Where's my eraser? What am I doing? I'm trying to write and speak and think at the same time. I have trouble doing any one of those. So 60 squared plus 80 squared, and we'll take the square root of that. So I have 3,600 plus 6,400, and that equals 10,000. So the square root of 10,000 is 100. And that works because that says my source voltage was 100 volts, and that's exactly what it is. It's 100 volts. So I end up having 60 volts dropped across my resistor and 80 volts dropped across my inductor. And I have 100 volts total added vectorially. That all works. And my impedance triangle says the same thing about the impedance. I have 30 ohms of resistance and 40 ohms of inductive reactance, and I ended up with 50 ohms of impedance, the total opposition to current flow. Later we'll talk about power. Power we would just figure in the same way. We have true power. Well, let's go ahead and talk about it. It's true power versus reactive power. So in this circuit, I have 60 volts times 2 amps. I have 120 watts of true power. And I have 80 volts times 2 amps, 160 volt amps reactive, 160 volt amps reactive, VARs. And again, they're added vectorially, so I can take the square root of true power squared plus reactive power squared. And take it from me, 120, 160, I'm going to end up with 200 volt amps. That's the hypotenuse, volt amps. That's the apparent power. And 100 volts times 2 amps equals 200 volt amps. How do you like that? That worked. So 60 times 2 is 120 watts. 80 times 2 is 160 volt amps reactive, VARs, and 200 amps volt amps. 100 volts times 2 amps is 200 volt amps. All right. Let's go back to our book and see what they're telling us. I don't like their numbers. They're using kind of crazy numbers, so I'm not going to bother because they're using 1500, 2512. They're ending up with an impedance of 2921 with 100 volts AC. So their math works. It's just a little bit difficult to follow. Oh, compute the value of the circuit impedance, which is equal to the vector sum of XL and R. And then they're trying to figure out what the phase angle is. They found the cosine of X of L divided by R. X of L divided by R is 1.67. So arctangent of 1.67 gives us a phase angle of 59.1 degrees. So if we take the cosine of that 59.1 degrees, we end up with 51.35% power factor, or 0.5135 cosine. We could have done it way back here where we had 1500 and 2512. We could figure out what this says. Actually, the cosine would be 1500 divided by 2921. That'll give us, that's adjacent over hypotenuse. So we use adjacent divided by hypotenuse. We'll do 1500 divided by 2921. And that'll give us the cosine, 51.35%. That's the power factor. Multiply it times 100 and express it as a percentage. It's 51.35%. The cosine of theta is 0.5135. And that's what they found out here, 0.5135. So find impedance using the cosine function. They did the resistance divided by the impedance, or you can say the impedance equals the resistance divided by the cosine of theta, and 2921. All right. You could also use the Pythagorean theorem discussed later in section 3.5.0. I think that's what we did. All right. So here's vector analysis. You know what? Let me blow this up. Why is that so small? You can't see that. There we go. So they have VR. That's the voltage across the resistor. And look, it's in phase. It starts at 0. And VL should be leading by 90 degrees. It is. There it is. And it ends up that the source, or the voltage total, is 50, what did they say, 58 degrees, 57 degrees out of phase? It's 57 degrees out of phase. Let's look and see. Oh, 59.1, okay. So it's 59.1, I'm going the wrong way, sorry. It's 59.1 degrees out of phase. That's what it is. So when they draw this, there. Why do I keep going the wrong way? There we go. When they draw it, they're drawing it 59.1 degrees out of phase. It's hard to see, but that's what they're doing. So it says voltage VL across XL can be considered as IXL voltage drop, just as VR is used for an IR voltage drop. A current I through X of L must lag the voltage by 90 degrees. Through an inductance, this is the angle between current and its self-induced voltage. All right, I'm going to move on. Sometimes they start talking, it doesn't make any sense. In a series circuit, the higher the value of the X sub L compared with the resistance, the more inductive the circuit is. This means that there's more voltage drop across the inductive reactance, increasing the phase angle toward 90 degrees. I was always told if it's a 10-to-1 ratio or greater, if you have 10 ohms of resistance and you have 100 ohms or better of inductive reactance, you can forget the resistance and just treat it as an inductive circuit. Vice versa, if you have 100 ohms or better of resistance and only 10 ohms of inductive reactance, you can pretty much ignore the inductive reactance and treat it as a purely resistive circuit. Here it says, at the opposite extreme, when resistance is 10 times as large as X sub L, the series circuit is mainly resistive. Phase angle of 5.7 degrees means the current is almost the same phase as the applied voltage. The total impedance is approximately equal to R, and the voltage drop across R is practically equal to the applied voltage, with almost none across X sub L. So here they're saying that the resistance is 10 ohms and the X sub L is 1 ohm, and the impedance is the square root of 101, so it's 10 point something ohms, but it's very close to 10 ohms. Here, when the resistance is 1 ohm and the X sub L is 10 ohms, it's pretty much an inductive circuit. You've got 10 ohms of impedance and 10 ohms of inductive reactance, and the phase angle is close to 90 degrees. It's 84.3 degrees. Let's see. Several combinations of X sub L and R in parallel are listed in Table 2. When X sub L is 10 times the resistance, the parallel circuit is practically resistive because there's little inductive current in the line. Okay. Small value of IL results from the high X sub L. All right. Let's move on. 2.4.2 RC circuits. RC circuits contain both a resistor and a capacitor. In a circuit containing resistance, only the current and voltage are in phase. In a circuit with pure capacitance, the current leads the voltage by an angle of 90 degrees. In an RC circuit that has both resistance and capacitance, the current will lead the voltage by some angle between 0 and 90. That should be a highlight. In a series RC circuit, the current I is the same as in X sub C and R since they're in series. Figure 22 shows a series RC circuit with resistance R in series with capacitive reactance X sub C. So there they are. They're in series. And here we have 100 ohms of resistance and 100 ohms of capacitive reactance. So that's pretty easy. That means theta is about a 45-degree angle. And we can take the impedance ends up to be 1.41 times resistance, or the capacitive reactance is 141 ohms. Figure 22b, the phase or rotating vector is shown in a horizontal position as the reference phase. This is because the current is the same throughout the series circuit. Resistive voltage drop IR has the same phase as the current. The capacitor voltage IX sub C must be 90 degrees clockwise from the current and the current through the IR, since the capacitor voltage lags behind the current. So where did they show that? Here it is right here. So there's the current through the capacitor and the current through the inductor. No, this is the parallel circuit. This is a parallel circuit. They're showing that voltage is on the x-axis because the voltage drops are the same across both the resistor and the X sub C. In a parallel RC circuit, the applied voltage is the same across each branch. Therefore, the branch voltages are equal in value to the applied voltage, and all voltages are in phase. Since the voltage is common throughout the parallel RC circuit, it serves as a common quantity in any vector representation of parallel RC circuits. This means the reference vector will have the same phase relationship or direction as the circuit voltage. Be careful, in a parallel circuit you cannot do an impedance triangle, because in parallel, when we're talking about purely resistance, the total resistance is less than the least resistor in parallel. And we cannot make an impedance triangle because we're saying that the hypotenuse would be the shortest side of the triangle, which is impossible. We can, however, figure what the current is through both of the branches, and then we'll use the current to make a current current triangle, excuse me. So that's what they're doing here. They're making a current triangle. 10 amps through the capacitor and 10 amps through the resistor, and 14.14 amps total in the circuit. As shown in figure 23, the phase angle is 45 degrees because the resistance and the X sub C are equal, resulting in equal branch currents. Phase angle is between the total current IT and the generator voltage VA. However, the phase of VA is the same as the phase of IR. Therefore, theta is also between IT and IR. There you go. So this gives us two ways. This is the equation for calculating the impedance of a parallel RC circuit. They say it's Z equals R times X sub C. That's product over sum. We're adding them vectorially. So to add them, we have to do the Pythagorean theorem. Square root of R squared plus X sub C squared. Product over sum. I like it better just to figure the current, find the total current, and then use that with Ohm's law to find the total impedance of the circuit. It's a little bit easier to do it that way. This is the impedance across the generator. The impedance of 7.07 ohms is equal to the resistance of the 10 ohm in parallel with the reactance of 10 ohms. Notice that despite what you might expect, the impedance of the equal values R and X sub C is not half. Instead, it is 70.7% of either value. When X sub C is high relative to resistance, the parallel circuit is practically resistive because there's little leading capacitive current in the main line. The small value of IC results from the high reactance of X sub C. All right. How long have I been blathering on here? LC circuits. Let's cover LC circuits. The inductive reactance and capacitive reactance are 180 degrees out of phase with each other, so you can just subtract the smaller from the larger. That's basically what we do. All right, I'm going to show you a series RLC circuit. Not LC, but RLC. Excuse me for a moment. Let me get rid of that. All right. Let's take a look at an RLC circuit. And I have to make the numbers jive here. Oops, wrong color. Let me make sure that I make this. Let's see, if I go like that, and I come up to a resistor, and I want this resistor to be 40 ohms of resistance, and then I'm going to go through this inductor, and through this capacitor. Now I'm going to make this 60 ohms of inductive reactance, and I'm going to make this one 30 ohms of capacitor reactance. So let's draw this vectorially. Our current is going to be all the same everywhere in the circuit. So this is going to represent the current total is going to represent the current through the resistor, the current through the inductor, and the current through the capacitor. I hope that I didn't run out of room. I hope you see that. All right. Now the voltage drops. This vector is going to be the voltage drop across the resistor. And since Eli the Iceman, this is going to be the voltage drop across the inductor, EL. And this is going to be the voltage drop across the capacitor, EC. Okay, notice they're 180 degrees out. And ice, current leads voltage in a capacitive circuit, voltage leads current in an inductive circuit. So basically, let's find out what our impedance is. I've got oops, wrong color. There we go. Impedance equals the square root of R squared plus, I'm going to open a parenthesis and say X of L minus X of C, close parenthesis, squared. These two are 180 degrees out. We're just going to subtract the smaller from the larger. So this is 40 ohms squared plus, this is 60 minus 30 squared. There, let me extend my page. So my impedance, and I have to make sure I put my square root symbol. My impedance equals the square root of 1600. That's 40 squared plus 60 minus 30 is 30 squared. That's 900. 60 minus 30 is 30 squared, 900. So my impedance equals the square root of 2500 ohms. So my impedance equals 50 ohms. So I can go back over here and I can say that I have a vector and it is 40 ohms of resistance. And I have a vector and it's 60 ohms of inductive reactance. And I have a vector that is 30 ohms of capacitive reactance. So I'm going to take this 30 ohms and subtract it. See, it's giving me the whole thing. All right, that's fine. I'm going to subtract that 30 ohms from the 60 ohms of X sub L, and I'm going to get a total of 30 ohms of reactance, X. And then we did Pythagorean theorem. We found 30 ohms and 40 ohms. We have an impedance of 50 ohms total. Now, let me see if I can grab all of this and move it out of my way. There we go. That's better. All right. So here's my 30 ohms of capacitive reactance. So we have a total ohmic value, an impedance of 50 ohms. So if I had a source voltage, I should have said this a long time ago, 100 volts divided by 50 ohms of impedance gives me a total current of 2 amps. There. So here I have 2 amps flowing through the resistor, and I have 2 amps flowing through the inductor, and I have 2 amps flowing through the capacitor. So if I want to find my voltage drops, it's 40 times 2, I have 80 volts dropped across my resistor. Look at this, I have 60 times 2, 120 volts dropped across my inductor. I only have 100 volts total, but I have 120 volts dropped across the inductor, and I have 60 volts dropped across my capacitor. That's because these two are 180 degrees out. Sometimes the voltage on this capacitor adds to the voltage across the inductor. So you can have 120 volts across your inductor at some points in the circuit, even though your total voltage source is only 100 volts. So here's that vector right here. So here's where we have the 80 volts, and we have 120 volts minus 60 volts equals 60 volts. And our hypotenuse ends up to be 100 volts. And we can find that, boy, this is a long page. The source voltage equals the square root of the voltage drop across the resistor squared plus, open or parenthesis, the voltage drop across the inductor minus the voltage drop across the capacitor, close parenthesis, squared. Okay, so that was 80 squared plus, open parenthesis, 120 minus 60, close parenthesis, squared. So, extend my page again. This page is 7 feet long. Square root of 80 squared plus 60 squared, 120 minus 60. So this is the square root of 6,400. The square root of 6,400 plus 3,600 equals the square root of 10,000. So my E source equals 100 volts. That works. So there it is in Pythagorean theorem form. Here's vectorially. You take the smaller and subtract it from the larger. They're 180 degrees out of phase with each other. You end up with 60 volts of reactive voltage drop at 100 volts, applied voltage, 100 volts applied. Sometimes they call it source voltage, sometimes they call it applied voltage. That's the voltage. All right, I'm confused. Let's go back to the book. So that's what they're showing here with inductance and capacitance. They're just going to subtract the small when there is current flow. In a series LC circuit, the voltage drops across the inductor and capacitor depend on the circuit current and the values of X sub L and X sub C. The voltage drop across the inductor leads the circuit current by 90 degrees, and the voltage drop across the capacitor lags the circuit current by 90 degrees. Using Kirchhoff's voltage law, the source voltage equals the sum of the voltage drops across the inductor and the capacitor with respect to the polarity of each. Since current through both is the same, the voltage across the inductor leads the voltage across the capacitor by 180 degrees. The method used to add the two voltage vectors is to subtract the smaller vector from the larger. Once calculated, assign the direction of the larger vector to the result, so it's either inductive or capacitive. When applied to a series LC circuit, this means the applied voltage is equal to the difference between the voltage drops EL and EC, while the phase angle between the applied voltage ET and the circuit current is determined by the larger voltage drop. Recall that X sub L is 180 degrees out of phase with X sub C. The impedance is then the vector sum of the two reactances. Their vector sum is found by subtracting the smaller one from the larger. Unlike RL and RC circuits, the impedance in an LC circuit is either purely inductive or purely capacitive. All right. The current and the branch of a parallel LC circuit are both out of phase with circuit voltage. The current in the inductive branch lags the voltage by 90 degrees, while the current in the capacitive branch leads the voltage by 90 degrees. Since the voltage is the same for both branches, currents IL and IC are therefore 180 degrees out of phase. The amplitudes of the branch currents depend on the value of the reactance in the respective branches. I apologize. We have switched over to a parallel LC circuit. I didn't even realize it. I was just reading and reading and reading. But anyway, that's why they're saying that the currents are out of phase, because it's a parallel circuit. The voltage drops are the same. With the branch currents being 180 degrees out of phase, the line current is equal to their vector sum. This vector addition is done by subtracting the smaller branch current from the larger. So, the impedance of a parallel LC circuit can be found using the following equation. I always like to find the total current and then just find the total impedance by using the source voltage divided by the total current. It's easier to do that way. This is x of L times x of c over x of L minus x of c. And for x of c larger than x of L, do x of c minus x of L. 2.4.2 RC circuits. In RC circuits that have both resistance and capacitance, the current will lead the voltage by some angle between 0 and 90 degrees. Oh, excuse me, wait a minute. I think I just read that. I don't know what happened here. Somehow I clicked something. I zigged when I should have zagged. 2.4.4 RLC circuits. Circuits in which the inductance, capacitance, and resistance are all connected in series are called series RLC circuits. Fundamental properties of series RLC circuits are similar to those for series LC circuits. The differences are caused by the effects of the resistance. So we did one of these already. I showed that you subtract the smaller from the larger between the capacitive reactance and the inductive reactance, and then you use Ohm's law, Pythagorean theorem to find the impedance between those two. So ER squared plus EL minus EC squared, there's your formula. And you can do the same thing with impedance. You can say the impedance equals the square root of R squared plus L minus C, or X of L minus X of C squared. First, calculate the combined voltage drop of the two resistances. As in pure LC circuits, this value is found by subtracting the smaller reactive value voltage drop from the larger. Okay. The angle between the applied voltage EA and the voltage across the resistance ER is the same as the phase angle between EA and the circuit current. The reason for this is that ER and I are in phase with each other. The impedance of a series RLC circuit is the vector sum of the inductive reactance, the capacitive reactance, and the resistance. This is calculated with the same method used for voltage drop calculations. So when X of L is greater than X of C, the net reactance is inductive when the circuit acts essentially as an RL circuit. Similarly, when X of C is greater than X of L, the net reactance is capacitive and the circuit acts as an RC circuit. I don't want to abandon you in your time of need. Read this. If you have any questions, please post them in the comments section. I'll try to answer them. I think we've gone over everything in one way or another. Parallel RLC circuits and vector diagrams. Total current is the square root of the current through the resistor squared plus IC minus IL squared. then you can find that total circuit current, and you can use that dividing the uh, total voltage divided by total current, and that'll give you the impedance of the circuit. It's a little bit easier to figure that way. All right. Think about it, AC circuits. The image shows a simple series circuit consisting of an on-off switch, a small lamp, motor, a capacitor. How would you classify this circuit? When energized, which components insert resistance, inductive reactance, and capacitive reactance into the circuit? Well, the light bulb is resistive, the motor is inductive, and the capacitor is capacitive. There you go. 2.0.0 section review. What's the voltage in a purely resistive circuit with a current of 22 amps and a 10 ohm resistance? Well, 22 times 10 is 220. Which of the following coils is likely to show the highest inductance? A coil with few turns, a coil with a non-magnetic core, a coil with a narrow coil, a coil with a short coil. They said the coil with a short coil. The total capacitance of three 10 microfarad capacitors and one 5 microfarad capacitor connected in parallel. We'll just add them together, 35. And a circuit's impedance is represented by the letter Z.